Hi, Summer Academy. So happy to be back with you today. In your last lesson, you learned about the first derivative test, which tells us about intervals where functions are increasing and decreasing, and also the locations of relative maxima and minima. Today, we're going to learn about something called the second derivative test. So I'm going to share my screen and go over with you example number 1. So in the Explore activity that you just completed, you uncovered these two key ideas. If the second derivative of a function, f double prime, is greater than 0, in other words, if it is positive on some interval from a to b, then the graph of f, the original function, is concave up on that same interval. Similarly, if f double prime, the second derivative, is less than 0 or negative on an interval from a to b, then the graph of f, the original function, is concave down on that interval. There is one more key term that we are going to utilize in today's lesson, which is this. If f double prime, the second derivative at some x value c, is equal to 0, and if the second derivative changes sign, so if the second derivative changes from positive to negative or from negative to positive, then the graph of f, the original function, will have something called an inflection point at that x value. If the second derivative is 0 and it changes sign, then we have an inflection point. So let's take a look at example number 1. Given f of x equals negative 6x to the 5th plus 10x to the 4th plus 12x minus 40, find, first, the intervals on which f is concave up and concave down. Okay. So what we learned in the Explore is that the second derivative of a function is what tells us about its concavity. So the first thing that we will need to do is actually calculate the second derivative of this function, which means first we need to figure out the first derivative. So I'm just going to write down our original function. F of x equals negative 6x to the 5th plus 10x to the 4th plus 12x minus 40. Okay, this is a fairly straightforward derivative. It's all power rule because this is just a polynomial. So let's find our first derivative. F prime of x is negative 6 times 5 is negative 30. Reduce the exponent by 1, x to the 4th. Then 10 times 4 is 40. Reduce the exponent by 1, so 40x cubed. And the derivative of 12x is just plus 12. And then that minus 40 is a constant. Derivative of a constant is 0. Awesome. That's our first derivative, f prime. Now we need to find our second derivative, f double prime, which again is just going to be power rule. F double prime of x is equal to negative 120, right? 4 times negative 30 is negative 120. X cubed. 3 times 40 is positive 120. X squared. And then the derivative of 12 is 0. So we just leave it off. Great. So similar to the first derivative test, we want to figure out where our second derivative is equal to 0. So let's turn this left side into 0 and solve for x. At what x values is the second derivative 0? So let's see, I can factor a 120 as well as an x squared out of each of these terms, which would leave me with a negative x plus 1. And then I can split this up into my two factors. So I know that either 120x squared equals 0 or negative x plus 1 equals 0. Well, solve for x. I'll divide both sides by 120, get x squared equals 0. I'll take the square root of each side, and I see that x equals 0. That's one of my x values. And then on the other side, let's add an x to each side. So then we're left with positive 1 is equal to x. So those are our two x values, where the second derivative is equal to 0. Fantastic. Again, really similar to the first derivative test, we're going to make a number line. And this number line is going to tell us about the sign of the second derivative, f double prime. So is the second derivative negative or positive? That's what this number line is telling us about. So I'm going to mark my two x values that I found, x equals 0 and x equals 1. And now I want to fill in each of those intervals. So from negative infinity to 0, from 0 to 1, and from 1 to positive infinity. I want to figure out on each of those intervals, is f double prime positive or negative? So the way that I do this, I like to go back to my factored form of the second derivative because I think working with the factored form can be a little bit easier. So let me just rewrite the factored form. F double prime of x is equal to 120 x squared times negative x plus 1. And now I want to pick a value in each of these intervals. So let's start with the interval from negative infinity to 0. And I want to pick an easy x value to work with. Usually 0 and 1 are the easiest x values to work with. Unfortunately, those are our two dividing points of our intervals, so we're not going to be able to use those. Let's try to pick the next easiest one. So for the interval from negative infinity to 0, I would pick probably x equals negative 1. That's going to be my easiest choice. Negative 1 is way easier to work with than like negative 2/3, right? Like, let's try to avoid fractions if we can. Okay, so I'm going to pick x equals negative 1 because it's in this interval. And then I'm just going to plug that point into the second derivative. So f double prime of negative 1 is 120 times negative 1 squared times negative 1 plus 1. Okay, so this is going to give me, well, 120. Let's see, negative 1 squared is positive 1. And then I've got minus a negative. I'll change that to plus a positive. So this is really 1 plus 1. Okay, each of these terms I already see is positive. So without even finishing simplifying this expression, I can see that this is going to give a positive value. That's all I care about is the sign of that number. So I know that on negative infinity to 0, my second derivative is going to be positive. Now we'll repeat that same process with our two remaining intervals. So next up, we have the interval from 0 to 1. Now, there are no whole numbers in between 0 and 1. I have to pick a fraction. I think the easiest fraction to work with is going to be 1/2. So I'll choose x equals 1/2. And again, I'm just going to plug that in to the factored form of the second derivative. So f double prime of 1/2 is 120 times 1/2 squared times negative 1/2 plus 1. Now again, all I care about is whether this number is positive or whether it is negative. So I know 120 is positive. 1/2 times 1/2, that gives 1/4. And then negative 1/2 plus 1 gives you positive 1/2. So again, I have 3 factors that are all positive. So without even multiplying it out, I know that this is going to return a positive value. So I'm going to mark this interval from 0 to 1 positive on my number line. We have one interval left from 1 to positive infinity. Okay, what's going to be an easy x value to choose to check this interval? Let's maybe pick x equals 2. Okay, and then again, we'll plug it in to our second derivative. F double prime of 2 is 120 times 2 squared times negative 2 plus 1. Let's try to simplify this a little bit. We get 120 times 2 squared is 4 times negative 2 plus 1 gives you negative 1. So now this one is a little bit different. I've got a positive times a positive times a negative. So this is going to return a negative result. So I will mark this interval negative on my number line. Now we are finally ready to respond to those 2 original questions. First of all, A, we want to find the intervals on which f is concave up and on which it is concave down. So I'm going to use this number line here. We know from the Explore that if the second derivative is positive, then the original function will be concave up. So to answer part A, f is concave up on the intervals where the second derivative is positive. So on negative infinity to 0 and from 0 to 1. Similarly, we know from the Explore that if f double prime is negative, that means the original function f is concave down. So f is concave down on any interval where its second derivative is negative. So that means from 1 to positive infinity. That takes care of part A. Part B asked us for the x coordinates of any points of inflection. Well, we learned that an inflection point or a point of inflection happens where f double prime is equal to 0 and where it changes sign. Well, we know from the math that we did that f double prime is equal to 0 at x equals 0 and x equals positive 1. So we have to look at those points and see where, if at any of those points, the second derivative also changes sign. So let's go back to our number line. At x equals 0, on the left-hand side, the second derivative is positive, and on the right-hand side, the second derivative is also positive. So it doesn't change sign at x equals 0. Therefore, x equals 0 cannot be a point of inflection. Let's look at x equals 1. For x equals 1, on the left-hand side, the interval on the left-hand side, f double prime will be positive, and on the right-hand side, it'll be negative. So it changes from positive to negative at x equals 1. Therefore, x equals 1 must be the location of an inflection point of f. So let's write that down. For part B, f has an inflection point at x equals positive 1. And this is because f double prime of 1 is equal to 0, and the second derivative, f double prime, changes sign from positive to negative. At this point. There you have it. That's example 1. We know now algebraically how to find intervals of concavity, intervals where f is concave up or concave down. And we do that using the second derivative. We're also able to identify points of inflection where the original function changes from concave up to concave down, or vice versa. You're going to get a chance to apply this now on practice set A. We'll come back together in a few minutes and look at another example. Awesome. Let's take a look at example number 2, because sometimes we're going to have functions that are not just polynomials. We might have other types of functions. We might have radical functions, or in this case, a trigonometric function. And we can also use the second derivative test to learn about these other types of functions as well. So example 2 is pretty similar to example 1. We're going to find the intervals on which g is concave up and concave down, and we'll also find the points of inflection. So we're going to start off the same way. We know that to figure out anything about concavity or inflection, we first need to figure out the second derivative of the function. So I know that g of x is defined as cosine of x, which means its first derivative, g prime, is negative sine. So its second derivative, g double prime, is negative cosine. Okay, now we want to know the significant points on this second derivative function. So we're going to see where g double prime, the second derivative of g, is equal to 0. Where is negative cosine of x equal to 0? With a trigonometric function like this, often I find it really helpful to just draw a sketch of the graph. So what does the graph of negative cosine look like on the interval from 0 to 2 pi? So I'm just going to draw a quick sketch. Well, I know that the graph of cosine of x begins at y equals 1. That's its y-intercept. So the graph of negative cosine of x must begin at -1. And then it will oscillate upwards and downwards, just like we know the cosine wave does. It'll look something like this. Not a perfect sketch, that's okay, but this is enough to get us the right idea. So we can use our sketch of our graph to figure out, okay, what x values does negative cosine of x equal 0? Where does this graph intercept the x-axis. And that, of course, is at pi over 2 and 3 pi over 2. And our graph here is going to help us figure out our number line really easily, right? So we'll make a number line. This number line is going to tell us about the sign of the second derivative, the sign of g double prime. And we'll mark just those two x values that we found, pi over 2 and 3 pi over 2. So I see on the graph that between 0 and pi over 2, our graph is negative. It's below the x-axis. So I'm going to mark this interval negative. Between pi over 2 and 3 pi over 2, our graph is positive. It's above the x-axis. So I'll mark this as positive. And then lastly, between 3 pi over 2 and pi over 2, this interval is below the x-axis. It's negative. Let's mark it negative. And we actually already have enough information to figure out our answers to part A and part B. So for part A, the intervals on which g is concave up, right? We know g is concave up if its second derivative is positive. So where is its second derivative positive? That's right, on this interval from pi over 2 to 3 pi over 2. So g is concave up on pi over 2 to 3 pi over 2. And we know that's because its second derivative is positive. Similarly, g is concave down when its second derivative is negative. So g is concave down on these two intervals that we marked negative, from 0 to pi over 2 and from 3 pi over 2 to 2 pi. And that is because its second derivative, g double prime, is negative. And then really quickly, our points of inflection for part B. We know for a point of inflection, we need to have its second derivative, g double prime, equal to 0 and a change in sign. So again, looking at our number line or at our graph, we can see that the second derivative is equal to 0 and changes sign at pi over 2, sorry, x equals pi over 2, and x equals 3 pi over 2. So g has points of inflection at those 2 points, x equals pi over 2 and 3 pi over 2. Cool. Now you've seen two examples of this second derivative test, and this is a topic that comes up a lot, not just in AP Calc, if that's what you're taking next year, but it comes up in college math classes a lot too. So go ahead and get some more practice in. You're going to head to practice set B and continue using the second derivative test to figure out both intervals of concavity and also points of inflection. You got this.